Powerful pulses of electromagnetic radiation are produced in pump lasers by Q switching and focusing. The electric field strength generated in these pulses can be as high as 1 billion volts per meter, and the pulses can be shorter than 1 picosecond, 1 millionth of a second. By circularly polarizing the laser light, we produce the conjugate product, which is a vector traveling in the direction of the laser, proportional to the square of its electric field strength, that is, up to 10 to the 18th volts squared per meter squared, generated in short, powerful pulses. The sign of the conjugate product is reversed if we change the laser polarization from right to left, but its strength is the same. The following sequences show the results of a computer simulation carried out at Cornell University's Center for Theory and Simulation in Science and Engineering. This video animation illustrates an important, newly discovered effect of the laser conjugate product on molecular dynamics: electric polarization in optically active molecular ensembles. A supercomputer simulation has demonstrated the ability of a circularly polarized pump laser to produce Zeeman splitting. We have dubbed this the laser Zeeman effect. The conjugate product vector, denoted by the Greek capital letter pi, has the same fundamental symmetry properties as the magnetic flux density vector B. Powerful circularly polarized pulses from a pump laser can therefore produce the spectral splitting and magnetization effects usually associated with static magnetic flux density. Well-known examples include the broadening and splitting of spectral absorptions, the Zeeman effect, nuclear magnetic resonance, and electron paramagnetic resonance spectroscopy. Almost 100 years ago, in his original experiment, Zeeman observed a broadening in the spectrogram of the sodium D line when he applied a powerful electromagnet. Conventional contemporary magnetic Zeeman effect apparatus permits finer resolution of spectral lines. If we replace Zeeman's magnet with pulses from a circularly polarized pump laser, we will see a similar pattern of splitting. This result has recently been demonstrated theoretically at the Cornell Theory Center, reported in the literature, and physical experiments are now underway. The laser Zeeman effect has the characteristics of the magnetically induced effect first reported by Zeeman, but appears at this stage to offer several additional advantages. Unlike a static magnetic field, a pump laser can be tuned. The laser's frequency can be adjusted to match natural absorption frequencies of the specimen, resulting in amplification of the spectrographic signal due to resonance. This technique allows us to investigate the nuclear hyperfine structure, the interaction between the electrons and the nucleus. To achieve this tuning, we can use different pump lasers, for example a solid-state laser in the visible light range, a carbon dioxide laser in the mid-infrared range, or a dye laser. Another advantage of the laser Zeeman technique is that it gives information on a different fundamental molecular property, the angular or electronic orbital spin polarizability. This is a vector which has the same fundamental symmetry as the magnetic dipole moment and is quantized in the same way through a new fundamental constant related to the gyromagnetic ratio. Because pulses from a pump laser can induce effects similar to those of a magnetic field, it is relatively easy to devise new technologies such as laser NMR and laser EPR by replacing the magnet with powerful circularly polarized electromagnetic pulses. To measure the effects induced by the laser conjugate product, a laser NMR or EPR device will employ a dual laser pump probe system containing a circularly polarized pump laser operating in the visible or mid-infrared frequency band parallel to a gigahertz or microwave frequency probe laser. The pump laser induces Zeeman absorption lines. The probe laser is then tuned to a resonance frequency matching the nuclear hyperfine structure, revealing the fine details of the spectrum. This fine tuning reveals much more detail than in conventional NMR due to Landé coupling between the nuclear spin quantum number and the electronic spin and orbital quantum numbers. Considering the vast amount of work carried out with conventional NMR, there is reason to be optimistic about the potential of laser NMR and EPR. Initially, these techniques may be used to study material in the gas phase using the well-developed techniques of ultra-high-resolution spectroscopy developed at MIT. The laser Zeeman effect and the NMR effect are sustainable in all types of molecules, both chiral and achiral, as well as in ensembles of single atoms. This animation shows the effects of frequency-dependent electric polarization, the electric counterpart of the laser Zeeman effect. The effects of simulated pulses from a circularly polarized pump laser on the motions of chiral molecules in the liquid state will be clearly seen. The size of the cubic laboratory frame, containing 108 molecules of the specimen being studied, is 48 angstroms on a side, or about 1/1000th of a meter. The duration of each laser pulse is only a few picoseconds, that is, only a few million millionths of a second in duration. Each time step in the simulation is 10 femtoseconds, or 1/100th of a picosecond. As molecules move to the edge of the laboratory frame, they are made to reappear on the opposite side of this cubic frame of reference. Thus the same 108 molecules are always present, and the density of the ensemble remains constant. The migration from one side of the lab frame to the other is represented visually as a continuous fading in and fading out of molecules at the boundaries of the lab frame. To investigate and illustrate phenomena of such small size and short duration, we use the Cornell National Supercomputer Facility's IBM 3090-600J supercomputer complex as both a numerical microscope and as a movie camera. In addition to computing the changing positions of the molecules, this simulation has calculated a number of vector values for each molecule. These vectors are net torque, molecular angular momentum, net force, and center of mass linear velocity. The rotational velocity and molecular orientation tensors are each represented by sets of 3 vectors. These vector values are shown as 3-dimensional arrows originating at each molecular center of mass. In each vector animation, we show the molecular ensembles first from the point of view of the laser, that is, looking down the z-axis. During the animation, the lab frame is rotated 90 degrees to show the ensembles from the side. From this point of view, the laser is propagating across the width of your screen. In the first example, the vectors in the baseline or no laser condition are scaled to the same maximum as the high-frequency laser. However, because the absolute magnitude of the vectors is much greater in the laser treatment condition, we must rescale the baseline vectors to make them visible. As a result, it is meaningful to compare the relative motions of the vectors in the two conditions, but not their relative lengths. The circularly polarized laser travels in the direction of the z-axis of the laboratory frame, producing a torque or twisting force on each molecule. This torque causes each molecule to spin or precess around its own z-axis at a frequency called the laser Larmor Frequency. The laser Larmor Frequency appears as a sharp peak in the infrared spectrum. This precession is an important phenomenon because it magnetizes the sample through the Inverse Faraday Effect. The circularly polarized laser thus acts as a magnet and can be used as the basis for optical NMR and EPR spectroscopy. In the baseline or no laser condition shown on the left, we see only random thermal motion of the molecules and no correlation of net torque in the ensemble. In the presence of a high-frequency pulsed laser, however, the precessional motion is clearly seen, superimposed on the thermal background. This extra spin lasts only as long as the laser pulse. Cross-correlating the x and y components of the net torque vector helps to clarify the rotational motion in the ensemble. This graph shows the time-lagged cross-correlation of two components of the 3-dimensional vectors we have just seen. The height of a point on the time correlation curve represents the degree of correlation for the entire ensemble. The lag time, shown on the horizontal axis, is the amount of time between the two measures of the vector components. For example, we plot the value of y 8 time steps later than the value of x for each molecule. The time correlation function has a prominent peak at a lag of 8 time steps, and the scattergram clearly shows the high degree of correlation. Only random motion is seen in the no laser condition, while a dramatic rotational effect is visible when the ensemble is subjected to a high-frequency circularly polarized laser. When we plot the x component 8 time steps later than the y component, the scattergram rotates in the opposite direction, since the time correlation function for x lags y is 180 degrees out of phase with the function for y lags x. Because torque is the time derivative of angular momentum, we can observe similar precessional effects for the angular momentum vector. The time correlation functions for this vector are shown in the appendix to this video. This laser-induced magnetization occurs not only in chiral ensembles, but in achiral media, such as water or ethyl alcohol. If the circularly polarized laser is directed with a fiber optic cable into a conventional NMR spectrometer, the extra magnetization has an effect on the NMR resonance frequency, shifting it upscale and increasing the effective resolution of the spectrometer. The prototype experiment of this kind was initiated at Princeton University in late 1990 to test this supercomputer simulation and theory. For this simulation, we have used the S enantiomer of bromochlorofluoromethane, a handed or chiral molecule. Chirality means that the molecule as a whole is non-symmetric about its center of mass, and thus it can sustain the electric polarization induced by the pump laser's conjugate product. By contrast, water molecules, for example, are achiral or symmetric, and cannot sustain the conjugate product's electric polarization. The orientation of three-dimensional bodies like molecules may be specified by a tensor, or a set of three orientation vectors, measured from the center of molecular mass, here shown in blue. The direction and value of these vectors is specified with respect to a laboratory frame of reference. Each of the three orientation vectors may be factored into three components, x, y, and z, also measured from the center of molecular mass in the lab frame of reference. As the molecule tumbles in three-dimensional space, the lengths of these vector components change. We will use the x and y components of orientation vector 1 to illustrate molecular orientation behavior in the presence of a pulsed laser field. Frequency-dependent electric polarization of chiral molecules suggests the possibility of many new effects recently reported in the literature, including nonlinear dielectric relaxation produced by pump lasers. Dielectric relaxation measures the Fourier transform of a function of molecular orientation called the time correlation function. The following sequences will illustrate this time correlation function for an ensemble of 108 molecules of bromochlorofluoromethane. For each molecule, the x component of the molecule's orientation vector 1 is plotted on the horizontal axis at time t, the current elapsed time shown on the clock. On the vertical axis is plotted the value of the y component of the same orientation vector, which is measured at time t plus lag. The lag time is shown in the lower left of each scatter plot. That is, for each molecule, we plot the x value against the same molecule's y value measured at a later time. All times are given in picoseconds. To understand the behavior of the points plotted on these graphs, watch the motion of the single point plotted for the example molecule as the molecule tumbles and changes orientation. Note the shadows of the x and y components shown in black. The center of the graph is the origin at which both the x and y components are equal to 0. As the x orientation component grows larger in the positive direction relative to the lab frame, the plotted point moves to the right of the graph. As the y component becomes more negative, the point moves down, and so on. The range of each axis is equal to the value of the largest deflection encountered in the entire simulation. Translation of the molecule within the lab frame does not affect the position of the point on the plot, since each vector component is measured from the molecule's center of mass, not from the lab frame origin. Therefore, while the molecules in the simulation are free to move around within the lab frame, the plot shows only rotational transformations induced by the laser field. To emphasize the time difference between the two parameters being plotted, note that in most cases the value of y is taken from the same molecule at a later time than the value of x, except in the condition where lag time is 0. Here we see a lag time of 100 time steps, equal to 1 picosecond. The following animations illustrate the time correlation between molecular orientation components induced by the applied laser. Different sequences display the relationship between lag time and the degree of correlation. Each position along the time correlation function plot has its own pattern of motion, representing the extent to which the two orientation components are correlated at any given lag time interval. The first sequence shows the correlation with lag time equal to 0. Each sequence illustrates ensemble behavior over 600 time steps, or 6 picoseconds. Only random thermal motion is evident in the baseline condition in the left panel. Even in the presence of a laser, the correlation of orientation vector components is much weaker than for the net torque vector. Although this sequence is not as visually dramatic as we saw for net torque, the ensemble correlation is statistically significant. This sequence shows the correlation at a lag of 100 time steps. On the low-frequency laser graph, note the pulsing motion of the data points, which reflects the effect on individual molecules, and the general alignment along an axis from top left to bottom right, which shows the overall correlation of the ensemble. These effects can be picked out above the random thermal motions, which are animated in the left-hand panel in which the laser is turned off. This video animation provides a direct visual link between the effect of a pulsed laser, the molecular dynamical response in an optically active liquid, and the experimentally measurable dielectric spectrum of this response. This complex interaction is impossible to grasp merely by examining the molecular ensemble at any given point in time. We have animated the magnetization induced by a circularly polarized laser, a phenomenon which is potentially of great importance in high-resolution NMR and EPR spectroscopy of complex systems such as proteins. The laser is used as an extra magnet which has the effect of producing a blue shift in conventional NMR and EPR spectra, a shift to higher frequency, increasing the absolute spectral resolution of the instrument and allowing a much more detailed mapping of proteins through their hydrogen resonances. The laser has the advantages that it can be pulsed and tuned, leading to a variety of new nonlinear dielectric methods. Scientific visualization of hundreds of megabytes of numeric results produced by the supercomputer simulation has allowed us to view molecular motions and vector forces directly, and was critically important in our understanding of these complex dynamical systems. Because of their ability to perform and visualize complex simulations like this, the supercomputer and powerful graphics workstations may now be seen as readily accessible and important tools for performing spectral analysis.